Before diving in, one honest clarification, because it actually makes this story better rather than worse. Hubble did not literally catch a star exploding in slow motion, in the sense of somehow watching the actual physical detonation unfold gradually over years. That explosion itself happened in an instant, the way every supernova does. What Hubble actually captured is something almost stranger and considerably more beautiful, a genuine optical illusion built entirely out of real physics, rings of light appearing to expand outward across the sky year after year, long after the star itself had already finished exploding. It is called a light echo, and it is one of the rarest, most visually striking phenomena in all of observational astronomy, precisely because it requires an almost perfect combination of circumstances to actually become visible at all. This is the real story of what a light echo actually is, the specific exploded star that gave Hubble one of its most spectacular examples of this phenomenon ever recorded, and why watching it unfold really does feel like watching an explosion happen in slow motion, even though that is not technically what is actually happening at all. To understand why a light echo looks the way it does, you first need to understand exactly what happens when a massive star reaches the end of its life and explodes as a supernova. In the span of mere seconds, the star's core collapses catastrophically, triggering an explosion so powerful it can briefly outshine an entire galaxy, releasing an almost unimaginable burst of light and energy. In every direction simultaneously, a genuine flash spreading outward from the explosion site at the speed of light itself. For an observer sitting directly in the path of that initial flash, the supernova appears exactly the way you would expect. A sudden, dramatic brightening that peaks within days or weeks and then gradually, steadily fades over the following months, following a understood, predictable decline that astronomers have studied in detail across thousands of similar explosions. A light echo happens when that same initial burst of light does not travel directly to Earth in a single, uninterrupted path, but instead first strikes a cloud of interstellar dust sitting somewhere near the exploded star, dust that happens to be positioned off to the side of the direct line between the supernova and Earth, rather than sitting directly between the two. When the supernova's light strikes that dust cloud, a small portion of it scatters, essentially bouncing off the dust particles in a new direction, some of which happens to be aimed toward Earth, because this scattered light had to travel first from the star to the dust cloud, and only afterward from the dust cloud onward to Earth. It takes a longer indirect path than light traveling the direct route, arriving at our telescopes later, sometimes months or even years after the original flash first reached us. This delay is precisely what creates the illusion of gradual, expanding motion. As time passes, following the initial explosion, the scattered light reaching Earth originates from progressively more distant rings of dust surrounding the star, each one slightly farther away than the last, because light striking dust at greater distances takes correspondingly longer to complete its full journey to Earth. Photograph the same patch of sky repeatedly over a period of months or years, and you capture a genuine, real sequence of images showing an apparent ring of light steadily growing larger and larger, expanding outward from the position of the original explosion, purely as a consequence of which specific layer of surrounding dust happens to be reflecting detectable light back toward Earth at any given moment. Stack those individual images together into a single sequence, and the resulting animation genuinely does look remarkably similar to watching an explosion unfold in dramatic, gradual slow motion, even though what is actually being recorded is an echo, a delayed reflection of light that had already finished its original near-instantaneous burst years earlier. The specific supernova that produced one of the most spectacular examples of this phenomenon Hubble has ever captured is designated SN 2016 ADJ. First detected in February of 2016 within Centaurus A, a well-known, relatively nearby galaxy sitting somewhere between 10 and 16 million light-years from Earth, itself famous among astronomers for the enormous, dark, dust-filled lane that cuts directly across its visible structure. A research team led by Professor Maximilian Stritzinger of Aarhus University in Denmark, working alongside astronomers from Dublin, Barcelona, New York, and Germany, spent 5.5 years using Hubble to continuously monitor the region surrounding this specific exploded star, patiently documenting exactly how the resulting light echo evolved across that entire span of time. Stritzinger described the resulting dataset in genuinely enthusiastic terms, calling it remarkable and explaining that it allowed his team to produce strikingly vivid, colored images and animations, documenting the evolution of these light echoes across the entire 5-year observation period, a phenomenon he noted had previously only been documented in a small handful of other supernovae throughout the entire history of astronomy. Morgan Fraser, an astrophysicist at University College Dublin who co-authored the resulting research, offered a specific, important observation about why this particular discovery was possible at all, one worth appreciating given how much recent attention has focused on newer, more advanced instruments. Fraser noted directly that while the James Webb Space Telescope has understandably drawn considerable public attention since its own launch, its older predecessor, Hubble, continues to provide genuinely incredible images of the universe, adding that Hubble has now been observing the sky continuously for well over 3 decades, a sustained operational lifespan that specifically allows astronomers to study exactly this kind of slow, multi-year phenomenon, one that would be essentially impossible to properly document using any newer instrument that simply has not yet accumulated enough years of continuous observation. Luis Galbany, an astrophysicist at the Institute of Space Sciences in Barcelona, who also contributed to this research, provided crucial context about the actual physical scale and violence of the underlying explosion itself, information that helps put the more gentle, gradual appearance of the light echo into proper perspective. Galbany explained that the genuine blast wave produced by this specific supernova explosion was racing outward at speeds exceeding 10,000 kilometers per second, an almost incomprehensibly violent, genuinely instantaneous event. Even though the visual echo effect Hubble spent years documenting appears, by comparison, to unfold with a slow, almost gentle, deliberate grace entirely disconnected from the actual speed of the underlying physical explosion that originally produced it. What made this particular light echo so exceptionally well suited to detailed study was the specific structure of the dust surrounding it. Centaurus A's own famous dust lane, the dark band of obscuring material that gives the galaxy its distinctive visual appearance, provided an unusually dense, extensive field of scattering material for the supernova's original light to interact with, producing multiple distinct rings of light that Hubble's instruments could track clearly across the full 5.5-year observation period. Researchers studying the resulting data found that this dust was not smoothly, evenly distributed throughout the surrounding space, but instead appeared to be arranged in distinct columns separated by considerable gaps, a structure the research team compared directly to a block of Swiss cheese, full of holes interspersed among denser, more concentrated regions of material. This finding carried genuine additional scientific value beyond the light echo phenomenon itself, since the specific pattern of light and shadow created as the echo passed through this dust field allowed astronomers to map the underlying 3-dimensional structure of that dust in a level of detail that would have been extraordinarily difficult to achieve through any other observational technique. It is worth understanding that SN 2016 ADJ is far from the only example of this phenomenon Hubble has successfully documented across its more than 3 decades of continuous operation, and comparing it against an earlier, similarly studied case helps illustrate both how rare and how genuinely valuable these specific observations actually are. Back in January of 2014, a separate supernova, designated SN 2014J, exploded within the galaxy M82, sitting roughly 11.5 million light-years from Earth, notable at the time for being among the closest supernovae to Earth detected in several decades. Hubble spent more than 2.5 years from 2014 through 2017 tracking that explosion's own resulting light echo as it bounced off a separate giant dust cloud stretching somewhere between 300 and 1,600 light-years outward from the supernova itself, producing another genuinely striking sequence of expanding rings that astronomers similarly compiled into a continuous, multi-year animation. The genuine rarity of this specific phenomenon deserves real emphasis, since it is precisely what makes any newly documented example, whether SN 2016 ADJ, SN 2014J, or any future discovery like them, worth this level of sustained scientific attention. Producing a clearly visible, well-documented light echo requires several specific conditions to align simultaneously. A supernova bright enough to produce a genuinely powerful initial flash of light, a sufficiently dense, well-positioned cloud of interstellar dust sitting nearby, though critically not directly between the star and Earth, and a telescope capable of monitoring that same specific patch of sky repeatedly with sufficient sensitivity and image resolution across the multiple years typically required for the resulting echo to become clearly, unambiguously visible. Most supernovae never produce a detectable light echo at all, either because no sufficiently dense dust happens to be positioned correctly nearby, or because any resulting echo is simply too faint for existing instruments to reliably detect and track across the necessary timescale. This is precisely why Fraser's specific observation about Hubble's own extended operational lifespan carries such genuine scientific weight. Newer, more advanced telescopes like the James Webb Space Telescope offer superior resolution and sensitivity across an important range of wavelengths, capabilities that have already produced numerous genuinely significant discoveries of their own throughout the earlier chapters of this exact series. But detecting and properly documenting a phenomenon that specifically requires several consecutive years of consistent, repeated observation of the exact same patch of sky is a task particularly well suited to an instrument with Hubble's own considerable operational history, now stretching across more than 3 decades of continuous service since its original 1990 launch, giving it a uniquely valuable capacity to study slow, gradually unfolding phenomena that a newer telescope, however more advanced in other respects, simply has not yet had sufficient time in orbit to properly capture. It is worth being completely clear about exactly what all of this means for how to properly understand a story like this one, since precision here genuinely enhances the wonder involved, rather than diminishing it. Watching an animation of SN 2016 AJ's Light Echo genuinely does feel like watching a star's explosion unfold in dramatic, gradual slow motion, expanding rings of light growing steadily larger across successive frames. But what is actually being documented is not the explosion itself slowing down in any physical sense. It is a delayed, indirect echo of light that had already completed its true, violent, genuinely instantaneous journey years earlier, now simply arriving at Earth's telescopes in a carefully staggered sequence determined entirely by the varying distances separating different layers of surrounding interstellar dust from the original explosion site. The explosion itself happened in an instant, exactly the way supernovae always do. What Hubble spent 5.5 years documenting was the universe's own natural delayed reflection of that single, violent moment gradually revealed to us one expanding ring of scattered light at a time. So here is the honest, complete picture behind what genuinely makes the story worth telling properly. A massive star in a galaxy millions of light years away exploded in a genuine, violent instant, its blast wave racing outward at more than 10,000 kilometers per second. That explosion's own initial burst of light reached Earth, was observed, and faded within the ordinary time frame astronomers expect for any supernova. And then, for the following 5.5 years, patient, continuous observation, using one of humanity's oldest and most enduring space telescopes, revealed something considerably rarer and more delicate. A genuine echo of that same explosion, scattered and delayed by clouds of ancient interstellar dust, arriving at Earth in a carefully staggered sequence that, once compiled into a single animation, does genuinely resemble watching a star's own death unfold in slow, deliberate motion. An illusion built entirely out of real, well-understood physics, and one of the rarest, most visually striking phenomena the science of astronomy has ever managed to document. If you want to see the next rare light echo Hubble manages to capture as it continues its 4th consecutive decade of operation, subscribe and turn on notifications, because this aging telescope has already proven it can still find things no newer instrument has yet had enough time in orbit to discover.